if you can develop microphysical or micromechanics model, multi-scale model, then you can use computer code cheaper on your desktop, and you can perform these calculations and minimize the number of experiments and save the cost. The thing is that without experiment, like, you can't get away. You have to do experiments. Okay, these are the parameters. Most of them are properties. See, your model has got a lot of properties as parameters. That's the good news, because you can do experiment and measure them directly. But if your model is all calibrated parameters, cannot be measured experimentally, then you've got problem. What is the problem? The problem is you have to assign values. How do you assign values? You have to do validation simulations and then assign values. Just because one experiment you predicted the right value doesn't mean that you go to another experiment with higher velocity and you may not predict correctly. So those are the complexity and issues. Okay, then this is a summary of the N model. Then let's go to Goda and Girard model. They are Italians, and they wrote the paper in 2021. Notice that, 2021. So this field is still fertile. You want to develop a PhD thesis topic? Here is a topic. You come up with your own GRP model, improve the existing model, or you develop from scratch. And you can do simulations. You have access to codes. DRDL, DRDO, DRDL, all of them have codes. They have access to Abacus and LS-DYNA. So you can perform a lot of simulations. Now, what they did, now they looked at body armor. See, remember my first view graph, we used aluminum as the substrate to model. But the real body armor is composite substrate. So unless you have a good model, you cannot simulate, you cannot design body armor for the soldiers. You want to reduce the weight of the armor, we spent $35 million. We couldn't reduce it through experiments from 6 pounds to 5.8 pounds. That was in 2000 to 2008. I was in the panel member for US Army. And so they spent $35 million to come up with reduced body armor. And we couldn't do it. So, but then with the computer, with the advent of computing capabilities on desktop with several workstations, you guys can put together a cluster, and you don't need a mainframe computer. Like when I was in IIT Kanpur, they had, as a graduate student, I did the frequency analysis of SLV3 rocket for random vibration. Because when the SLV3 was mounted on the umbilical tower in Sriharikota, there's so much gust wind that it was waving, and it had, I don't know what exact problems the ISRO faced, but I did the frequency analysis under Dr. N.C. Incam. So here, a cylindrical rod is penetrating a ceramic backed by a composite layer. So in 2021, we can do it now. The project started in 1990. It took 30 years to have a model. I'm not saying this is the model. I'm saying at least there is something going on, okay? Okay, now if you look at this, again the same like the other model, N model. It looks kind of different, but it's the same. If you watch the initiation function is, again, the local stress equal to the applied stress. This is a Macaulay bracket. So if sigma 1 is positive tension, divide by 1 minus d1, like omega 1, d1, and then this is under tension plus under compression, another d1 minus or omega 2, and then under tension in the other direction, and then compression in the other direction, and then the shear in other directions, and you have a surface, fracture surface. You begin with lambda equal to 1, and then phi increases, phi is the applied load, and then the damage start growing, okay? It's the same thing. It looks very different, but both models are very similar. This is more simpler model than the N model. Okay, they looked at this configuration, and then they performed simulations, and they came up with constants, And then this is what they did. Oh, wait a minute. This is same model. Maybe it's a wrong view graph. What did I do? I went too far. Ah, I think, am I going backward? Yeah, but, oh, sorry, got lost. Ah, Goda model, okay. Right, so now, there is an initiation, damage initiation equations, 5 equations, right? Simple, this is stress. When applied stress exceeds the strength of the tensile strength, damage initiate. Big deal, right? You can do the test, you know the strength, and the abacus will calculate the local stress. And then same thing in tension, compression, shear. You have shear strength measured from experiment, compressive strength, tensile strength. So you can move on with the damage initiation. How about growth? Growth is always empirical. There's no physical model, and growth is so complex. Single crack is big deal, single crack you can follow, but it is million cracks and million defects. Now here, they assumed this expression for damage evolution. Again, when lambda equal to 1, see I for different mode. If you have 8 modes of failure, D1, D2, D3, D8, and then you calculate lambda 1 up to lambda 8 and whatever, and when lambda is 1, 1 minus 1, 0, this term become 1, 1 minus 1, 0, 0. Same thing. N model looks different, but it's the same thing. So, but different equations. Like that, compare N. Omega equal to 1 minus e to the power of that. R equal to 1, 0, 1 minus 1, 0. Same thing here. So, in a sense, all these CDM-based models, they have set of initiation equations. You can get it from open literature, or you propose in your PhD thesis, hey, by the way, I'm not happy with the Hashin model. You do some experiment and validate it and propose an equation for damage initiation. Now, damage growth, nobody will kill you if you change this equation. Big deal, you can change this equation based on your research, your finding, your invention, innovation, whatever it is. So there is an initiation criterion, growth criterion, strain rate dependency, and then you degrade the modulus. That's all, the 4 methodology that makes the composite model. You can introduce all type of failure and capture the failure damage mode with the appropriate equation and perform experiment, calibrate the constants, and tune the constant with the code simulations, and you are moving forward. And again, see that? Same thing, right? Young's modulus, shear modulus degraded. This is the plane view. Plane view, you have 2D model. Okay, but then the built up is 3D. All right. One thing these people did, the energy partitioning. They tracked all the energy due to friction in the interface between the 2 plies, right? Delamination, energy goes to delamination, energy goes to rupturing the fiber, energy goes to fiber bundle sliding failure. So all this damage model consumes energy. So the kinetic energy, the projectile's kinetic energy is the total energy is going to be dissipated, dispersed through wave propagation and damage, deformation, and you keep track of them. Now, you get wrong result if you don't keep track of the energy correctly. If you lose energy, that means you are doing something wrong. When you do abacus calculation or any code calculation, keep an eye on energy term. You might have put some wrong parameters, inadvertently, and then what you do is just to make sure that your calculation is correct and you are getting realistic and meaningful results. Okay, so you can see that energy, the total energy is the horizontal line, and then the kinetic energy of the projectile is coming down, and then different color shows how much energy is spent on each damage process. And this tells you clearly where the energy goes. If you are a body armor designer, you want to see where the energy goes. So So the parameters. And they simulated about, 4 experiments, and they showed 600 and 400 meter per second the penetration of the cylinder, and they examined the cavitation in the front, cavitation in the back, and then they compared with experiments, okay? And this is the summary of the model, right? Now let's go to the last one. The last one is a hyperelasticity model. Why do we need hyperelasticity model? Because the fiber could be polymer fiber. When a projectile hits the target, the back surface of the target is going to bulge. When it bulges, the fiber is stretching. It could stretch up to 100%. So I have seen some experiments with high-speed camera. The back place, they just bulge. And so then how can you use just a simple elasticity model for the fiber? For carbon, I can understand it, brittle carbon, it breaks. But then for polymer fiber like polyethylene, polycarbonate, S2 glass, not glass, fiber. So, but then the glass fiber also has more ductility. It has been, there is a table which I have seen, the amount of stretch in glass fiber is also high, even though you call it glass fiber, but it has got ductility. So we published 3 papers. This is the model that my students used it and published paper. You can see that I had 2 master's students, one from Australia, one an American student, and one used Yale 3D, the other guy used Abacus. So where do you begin? You begin with, what time is that? I'll try to wrap it up in 10 minutes. Okay, many of you know that constitutive equation can be derived from using either Gibbs free energy function or Helmholtz free energy function. Helmholtz free energy function is a function with a function of strain stretch tensor, whereas Gibbs is stress tensor. So when you differentiate this psi with respect to strain, because this is Helmholtz free energy, you can, hello, you can just move this. Something else. So anyway, so what happened when you do your PhD thesis, that you either begin with Gibbs energy or Fredholm energy. You go through the literature. I could have given another paper on micromechanical model for brittle materials developed by the famous people like Sia Namath Nasser and several others. They used like a casting in Los Alamos National Lab, and they all used either Gibbs energy or Helmholtz energy, free energy. So then once you take differentiation, if you know partial differential equation, differentiate the function, you get constitutive equation. Stress related to strain or strain related to stress. Once you derive the constitutive model, then it has got 2 terms. First term is shear term. Shear term is what? Volume doesn't change. It is called shape change, but volume doesn't change. That is captured by shear modulus term. The second term is bulk modulus term. That's a volume change. That's where in high pressure, high strain rate, high pressure problems, you need the equation of state. That equation of state is related to bulk modulus and volumetric strain. So, okay. So, once you have the constitutive relationship derived from the free energy relationship, now you introduce continuum damage mechanics like the other guys did. What did they do? They multiplied E by 1 minus D, right? And G by 1 minus D. But this is a 3-dimensional equation. So, but you have to define what D is. The D can be the constitutive equation. They introduce different Ds. And so this model is very similar to the other 3 models, except they introduce explicit terms for fiber. And it is unique because nobody else have done that. So I wish it comes back. So you have 4 terms. Any free function, you have 4 terms. Xi equals the first term, shear modulus term, which is shape change, not volume change. They sometimes call it isochoric thermodynamically. The second term, volume change, the bulk term. Third term, fiber stretching. Fourth term, fiber stretching. And fourth term is shear, under shear. Third term is under compression and tension. So the function has got failure of the matrix and the failure of the fiber explicitly appears in the 3-dimensional constitutive equation. Okay, good. So you can see the first term, shear modulus. Second term, bulk modulus. And since it's a hyperelasticity model, beta is the Ogden parameter. And this term describes rubber-like elastic material where the stress strain curve suddenly after some strain goes up vertically up. So the beta captures that. J is the Jacobian, that is the volume, right? Jacobian. And this is the fiber. I4 is the invariant that describes the stretching of the fiber system 1. Then fourth term describes stretching of the fiber system 2. But in most of the composite, they don't use 2 fiber. They don't use S2 glass fiber and Kevlar fiber. They use only 1 fiber system. Because of that, the fourth term would disappear, okay? Now we differentiate that equation, you get constitutive equation. This is the one, okay? That's just the derivation of the differentiation of the previous term. Now you use CDM. That means the first term, shear modulus, I'm going to degrade using 1 minus d to the power of m. Bulk modulus, again, degraded by 1 minus dm. That means matrix expansion or matrix contraction. Third term, that's a KD for the fiber. DF1 is for the fiber. Damage for the fiber system 2. Damage due to shear. So you got DM, DF1, DF2, DFS, and then you define them. And you will be surprised. You go back to the same equations. The N are Goddard and Goddard equations. So strain-based damage initiation here. R, here we are using R as the initiation parameter. The initiation for matrix under shear cracking equals to 1 Mises strain, which is equivalent strain, divided by material property, the strain at which you start seeing cracks in the matrix. So you can experimentally obtain this epsilon ms. So a simple strain ratio describes the initiation of matrix cracking. Okay? Now you can see that the different fiber system, the strain at peak, the last column, is different for different fiber system. For glass fiber, it has got 4.73% of stretch. So, and the next thing, under compression, you can fracture the matrix material using this relationship, where J is the Jacobian and JME is the material parameters. And then delamination, this uses Hashin's model, okay? It's a familiar model. And then the growth. Come back, some of you may have good memory power. The N model, the other models I showed, that growth is an empirical model and is again exponential. You can see when R equal to 1, 1 minus 1, 0, exponent to the power 0, 1 minus 1, 0. So R equal to 1, you are initiating damage. When R is greater than 1, the damage is growing. And this equation captures. When R keep on increasing, the parameter iota controls the rate at which the growth occurs. The simple empirical model can do the job. So we implemented the model in both Yale 3D, which is an Eulerian code, and Abacus Lagrangian code. And we looked at two configurations. One is plate hitting a plate, which is a shock wave propagation. The other one is ballistic. And this is the fiber 2D plane fiber. You can obtain the elastic parameters by using ultrasonic. I know Dr. Gopalan is here. You give a small piece to him, he will give you those constants. You know, they have a fantastic measurement system in Indian Institute of Science. So, and we did this in Army Research Lab. And then we did the plate impact test. What is plate impact test? Most of you may not know. It's the slick, good scientific experiment. I think IIT Kanpur may have, or some other institution may have. It's very expensive. It's a very precise test. You hit one plate on another plate, and then you measure the back surface velocity, the visor, that's a target, GRP, and that's a flyer, steel or aluminum. It hits planar impact. All the material points move in one direction. All the other strains are zero. There is only one non-zero strain, which can be calculated from the measuring the velocity versus time of the back surface. So the back surface particle velocity versus time becomes the data. So now you look at three graphs. One for ceramics. So if the target plate is ceramic, you get something like this. Elastic, some transition to elastic plastic or elastic inelastic, and then you see the wave dispersion, you know, and then it reaches the shock stress that is controlled by equation of state, and then it releases. All right. This is silicon carbide, that is boron carbide. Now metals, same thing, elastic, and then you have Hugoniot elastic limit. That is the limit of elastic deformation is ceased, inelastic deformation occurs. In metal, it is plasticity, and in ceramic, it is micro cracking and dislocations, twins, and you see the elastic and then elastic plastic transition. And of course, this is spallation. You see, this spallation is a tensile failure in metal, and you won't see it in ceramic. See that? It doesn't go up. It comes down and goes up. That is spall signal. You see the ceramic, there is no spall signal because tensile strength becomes zero. This is composite, a mess. I would call it a mess. The data showed something low velocity, it showed elastic, and then a curve, and then shock stress. You increase the velocity, you again see elastic, and then some dispersion, serious dispersion. You should expect that, right? It has got a weave, it has got fiber, it has got dissimilar materials, it has got impedance mismatch everywhere, and it has got interface. So you expect dispersion, and that's what it showed, the plate impact test. Can we reproduce that using the so-called hyperelasticity model? We will see that. This is an experiment performed at Case Western University by Vikash Prakash with the funding from Army in 2009. So they did two tests, one thick composite, one thin composite. So the thin composite is 6.8 millimeter, and the thick composite is double. And then they got this visor trace or signal, and we tried to model this. We used Yale 3D, we got all the parameters, and then we did some sensitivity study. What is sensitivity study? You have parameters in your model. First you see how each parameter, when you change, how the particle velocity changes in your simulation. So here is an example. The one parameter, this is the damage initiation parameter under compression. And we said, this is important. When you put a material under compression in all direction, can you expand the volume? The specimen is compressed axially, laterally. Complete inertial confinement. Can you open up voids in brittle materials? Yes, you can. The mechanism is called wing crack mechanism because brittle materials have millions of flaws. Each flaw is a tiny crack. When you put them under compression, what happens? Locally at the flat tip, the stress is not compressive. It is tensile. So the applied mechanics people, see, this is a conference, applied mechanics conference. Applied mechanics people theoretically said, hey, by the way, brittle materials will fail. Bulk modulus will degrade under compression. Whereas equation of state under compression, bulk modulus increases. Right? Bulk modulus, whereas brittle materials under compression, it expands inside at the crack tip, the flat tip. So that means the bulk modulus is affected by degrade due to tensile crack opening at the tip. That's a mechanism invented or derived and proved by several people. Hori and Namath Nasser is one of them. So now let's do the sensitivity study. I got 3 values for this parameter. Okay, this is the Jacobian, so it's a volume under expansion, matrix volume. That's a constant. And you put 0.1, 0.5, 0.9, and the three graph or the curves. The dotted line is the experiment, LT48. See that it is not matching. So this parameter is less sensitive to, this parameter is insensitive. The model is insensitive to bulk modulus change, which makes sense. But still, you see the effect, slight effect. Okay, let's go to the next one. Now, this is matrix cracking under shear. Look at that. The parameter, the growth parameter, iota, you change it, and look at the way it changes. Now, that's a Hugoniot elastic limit, right? And you can see that it's it significantly affects the profile. That tells you that matrix cracking is changing the profile. That means the GRP, when the matrix cracks, that you develop inelastic deformation, and the eye can be used to model that. The second term, which is the Ogden parameter usually used for rubber type material, it affects the free surface velocity when you changes the values. So you can see you get different type of thing, but this is the experiment. So what you do, you pick up that value for that parameter, beta. So the Ogden parameter, we chose -2 because that matched with the experiment. And goes on and on. Okay, this is element size study. If you are using for design of anything you are working on, that first you do some mesh. Your mesh can affect your result. So you don't just do one mesh and get some solution and move on. You try to do one coarse mesh, intermediate mesh, very fine mesh. If they get similar result, you are in good shape. And this is the simulation of the plate impact test of different velocity. You can see that very nicely. See that this is the lowest velocity, that's the highest velocity, and Hugoniot elastic limit, and you see the dispersions of the wave, and it reaches the peak that is controlled by equation of state. And also we did some diagnostic to see axial stress versus lateral stress, and you can examine. That's a damage. The lateral stress is constant and then it increases. This axis is damage, bulk damage. And 1 mean below 1 no damage, above 1 damage. You see that it's all below 1. So the bulk modulus is not changing much. Okay, this is the Hugoniot. If you are a shock physicist, you will understand. But initially what happened, this is the shock stress versus volumetric strain. You begin at 0 and you compress the material along this line. That's the original modulus, okay? See, it goes up. And then damage initiate, and you unload at that point, you come back here to 0. So eventually what happened, if damage occurred, the modulus, degraded modulus went from 22 to 17, okay? And then it is coming towards the hydrostat. Hydrostat is the pressure volume equation of state. It's 15.8 is the bulk modulus in the hydrostat. Whereas the slope of this is not square root of k over rho. The square root of k plus 4,3 g over rho, okay? So the wave speeds under uniaxial strain is different than the wave speed under uniaxial stress, is different than the wave speed under spherical wave. So you have to be very careful when you have to understand. So it's beautiful. The model is nicely taking in the original modulus, degradation of the modulus, and eventually it is reaching the hydrostat. And we performed all the tests and we matched the experiment. You can see that's the dotted line is the simulation, and then the, dotted line is the experiment, and then the solid line is the simulation. You see that it did well, but here it didn't do well. It's very complex because the viscous effects are dominating, and there's room to improve the model by introducing some viscosity parameters. So they all did well, relatively very well, because given the complexity of composite, you can't match exactly. And there is a statistical things also come into picture. You do 10 tests in GRP, you are not going to get exactly the same velocity versus time. Very similar, but the slope will be very different. So given that scatter in the experiment, I think the hyperelasticity CDM-based model able to reproduce shock wave experiments. So then we thought, okay, we got all the parameters, and then we thought, how about use the same parameters, these parameters, which we calibrated using plate impact test. Now let's do, can we predict depth of penetration in a ballistic test? So that is the ballistic test where the bullet stops at inside the target, and you can measure how much depth the projectile penetrated. And we have data for that, and we came up with a silly design. This design is bad, really bad. We got bad result, but later on what we did, we realized that this kind of expansion of fine won't work. You really want to have an accurate, realistic result from this code. Equal, all elements are equal. Doesn't matter the elements away from the location of the projectile, everything is same. The projectile and target aspect ratio of your element should be the same. You may end up with 2-3 million elements. One calculation will give you the right result. So right now we are doing about 5 million element simulation for GRP with the delamination criterion, and we expect to get very good result. So we did the simulation with uniform. This is uniform mesh, not the other mesh. The other mesh gave bad result. So this one, all uniform. See here? Same. Look at the resolution. Same. So this predicted and matched with the experiment. We calibrated 2 more parameters for the fiber. Okay? So in summary, I mean, there's room for the model. The CDM hyperelasticity model can be improved. And actually the fiber parameters we did not touch. But when I go back, there's a PhD student working on it. We want to look at the fiber failure more closely to make sure that we can make predictions. And the mesh design is important, right? Your erosion strain can create problems. The ply delamination, the friction between the plies, all are still out there. So I presented 4 models. All the models have connectivity. The initiation criterion, growth criterion, strain rate dependency, they're all the same. And the degradation of the stiffness, they are all the same. Only thing, each author used different types of equations, but the methodology is same. So if you are doing PhD in penetration mechanics, if you are looking at complex composite materials, here is a starting point. Go and grab all the papers, go through all the equations, grasp it, and then you make progress in your thesis. With that, thank you very much. Sorry I took a lot of my time, your time. Thank you. Some quick question, one or two questions? Any?
For example, most the phenomenon that we are trying to model is very complex, obviously, and therefore we have to go for empiricism. But the empirical models have limitations that they can only match up to what your experiments that you have conducted. And the reason why we develop models is to do predictions beyond what experiments do, and therefore the validity of empirical models, be in Johnson Cook or anything, is valid only up to the range where experiments are already done. So do you have any comments on this?
Yeah, sure. I mean, first of all, let me tell you, Dr. Lakshman Rao, that you cannot go away from empiricism. Empirical models will exist forever. Unfortunately or fortunately, the many empirical models, if they are calibrated properly, you can predict within that range like you mentioned. If the applied pressure is 5 times more than the pressure and the strain rate is 5 times more than the strain rate, then what happens? You get into trouble. You are extrapolating, but some case it may work if it's saturated at certain strain rate and it's not changing much after that, then you are okay. So you have to be careful. So this comment is definitely, I wanted to make it, but I did not. But you have to be careful. But then my point is, all microphysical model, micromechanical model will have empirical equations inside. You can't escape from that. Okay. Go ahead, yeah.
Yeah, I just wanted to know if something like this can be modeled with phase field, and if people
louder.
If something like this can be modeled using phase field modeling, and if people have actually done this, because I think phase field, because it's based on energy minimization, it might be less empirical. So
which model are you talking about?
The phase field fracture model, can it be used for modeling?
Phase field?
Yeah.
Oh, you are not, okay. I thought you were asking.
Yeah, not the ones that you talked about.
See, phase field, I had some experience, not in depth. That is useful for amorphous material, in my opinion. Glass type material, phase field model is good. But now people indiscriminately using phase field model wherever they want to. But you have to be careful. People are using phase field model in penetration too. I know that. But I won't use it unless, because if it is, the lattice is repeating, I don't know how much physics that phase field model has. That's a numerical scheme, right? Am I right, Tej? You have finite volume, finite element, meshless method, MPM, DEM, discrete element method, material point method, and MLPG meshless method, and FEM particle conversion method, and you have SPH method, you have Eulerian method, and you have arbitrary Lagrangian Eulerian method. I mean, I can go on and on and on this numerical code, and phase field is one of them. Okay.
Thank you.
Okay.
Taking the experimental parameters of unidirectional composites sort of thing. But when it comes to plane view sort of things, there is a warp weft going on King's sort of thing. There again the stress concentration build-ups actually.
Yeah, correct.
So
correct.
will these parameters will be countered in this?
Okay, good question. I didn't present it. Yen, what he did, Yen came up with 5 mode of failure, damage. Then he introduced another 7 for plane view. They are different equations. So you are right. Unidirectional, the damage, 5 damage won't work for your plane view. I skipped because of the lack of time. But I did mention extendable or modifiable to view, plane view. So the next guy, the Goddard, he came up with a ply 2D constitutive model. For each ply, there is a constitutive model. So that's why plane stress worked for him. And So plane wave damage mechanisms you have to include those type of equations. Yeah. Thanks for asking. Yeah. All right. I think in the interest of time, I'll stop it here. And
Hello. Just one last question.
okay.
Actually, you showed something about the energies during the impact problem. So can you comment on hourglassing energies in certain cases?
Hourglassing?
Yes.
I think that's again a good question. Hourglassing and the contact they put penalty function. There's some kind of penalty. And there they introduce artificially some numerical energy. See, these are the things, Dr. Gopalan. Yeah. So then they introduce, like what you said, artificial viscosity, right? And there they are smart enough. They keep the energy because they are spreading the singularity propagating. That's a sharp front. So they disperse it to few elements, right? They disperse it to few elements. But then they make sure the energy is conserved. Whereas the contact algorithm is tricky. They artificially add energy. And you have to remove that energy. In that view graph, there is one energy removed. That energy is due to the penalty function in the contact algorithm. Okay?
Thank you.
You're welcome. Yeah. Okay. All right.
If there are no further questions, I would like to thank Professor A.M. Rajendran for delivering an insightful lecture. Your expertise on modeling composite materials under shock and impact has definitely captivated our audience, sir, and has left an lasting impression. This talk will definitely provide an innovative perspective to all the young researchers who are working in the area of modeling. Sir, we are grateful for the time and effort you have put into sharing your long acquired expertise with us. Thank you for being an integral part of our conference. Now I request Professor Lakshman Rao, President ISAM, to come on to the stage and present a memento to our distinguished speaker, Professor A.M. Rajendran. Thank you, Professor Lakshman Rao, sir. Thank you, sir. So with this, we have come to an end of Professor L. Srinath Memorial Lecture. Now we will have a short tea break, which will be followed by invited lectures, technical presentations, and mini symposia in the seminar hall complex opposite to this building. So I request everyone to join for us at tea at seminar hall complex. Thank you. The next sessions will resume at 11:15 in the seminar hall complex.